Okay, so bond enthalpy is another way, essentially, of finding heat of reaction. And so you'll need this chart for this lesson. We actually don't need the top part of the chart. What we're going to be using is this bottom part that we've been ignoring up until now. But we're going to use the average bond enthalpies part of the chart to do bond enthalpy. So um, why are we doing another way of finding the heat of reaction? This way it actually connects to Lewis structures. So it's cool to see how the structure of the molecules involved in a reaction end up dictating whether that reaction is endo or exothermic. We're looking at what bonds are literally being broken and then reformed in a reaction, and how much energy is either used or produced during that process. It'll also connect nicely when we next time or later talk about energy profiles. You'll see this coming in again. So it's really a nice conceptual background. Okay, so you'll always know that I want you to use this particular method for finding heat of reaction when it says using bond enthalpy. So you don't have to guess. And we're given a reaction here. I wrote it out twice because the second time is just going to help me do what I need to do. Using bond enthalpy, find the heat of reaction for CH4 plus 2O2 yields CO2 plus 2H12. I need to, in order to look at what bonds am I breaking, what bonds am I making, I need to draw Lewis structures. If you need a quick review on Lewis structures, I also posted a super quick shortcut way of figuring out Lewis structures that is good enough for this lesson. But anyways, for each thing in the reaction, all of the reactants on the left and all of the products on the right, I need to draw their Lewis structure. CH4 is going to look like this. O2 is going to be a double bond. I don't care if you actually show all of the lone pairs. If they help you make sure your Lewis structure is correct, you can do that. But I'm actually going to draw it twice because this complete and balanced reaction says I have two molecules of O2. And then for my products, let me switch to a different color. CO2, again, I don't care if you show me your lone pairs, but CO2 looks like that. Water looks like this, and I'm going to draw it 2 times. So if you think about what's happening is we're taking the reactants, the CH4 and the O2, and we are breaking them down like they were Legos. Somebody built some Lego structures, but you want to build other Lego structures. So we literally break them down. We break all of the bonds in the reactants, and we always will. We will always break. Let's go back to purple. Sorry. We break bonds of the reactants, which are always on the left-hand side. And the products, we then have all these scattered Lego pieces. The products we're then going to build, we're going to form. We are going to form the bonds of our products. And it just so happens that breaking bonds is an endothermic process. That means it requires energy to be put into it. That should make some conceptual sense. If you think about having like a wooden board that you're trying to break, or 2 people are holding hands, they're bonded together, and you're trying to break them. You have to put energy into that process. Breaking bonds is an endothermic process, and therefore values on this side will be positive. Forming bonds is the opposite. So it doesn't make as much conceptual sense, but the truth is when you form bonds, energy is released, and therefore it's exothermic and negative. So we need to now account for all of the bonds I'm breaking and all of the bonds I'm forming. And this is the type of work you need to show all this work, frankly. I am breaking a CH bond there. I see a C bonded to an H. I'm breaking another one there, and another one there. So in total, I am breaking 4 CH bonds. If I'm looking at other reactants, other bonds I'm breaking this O double bonded to an O. And it's not 2 single bonds that I'm breaking. In my accounting, I'm going to look at it as that, what I just highlighted in yellow, is 1 double bond, and there is another double bond. So I am breaking 2 O double bonded to O's. Now, what bonds am I forming? I'm forming a C double bonded to an O and another C double bonded to an O. It doesn't matter like if the C and the O are on the left or the right. Sorry, to clarify, it doesn't matter that this O is to the left of that C and that O is to the right of that C. Someone asked me that once. What does matter is that we are dealing with things on the right-hand side of the reaction. That's how we know that we are forming bonds. So again, 2 C double bonds to O. And then also I am going to form an OH bond, another OH bond, another OH bond, another OH bond. 4 O single bonded to H bonds. That's how you show most of your work, but then to actually finish it up and get an answer, that's when we finally use this bond enthalpy chart. So you'll see it's, if I get rid of that, it's divided for you into single bonds and multiple bonds, like doubles and triples. You can use that multiple bonds section to help you out in terms of drawing your Lewis structures. Sometimes double or triple bonds aren't an option if you don't see them in that chart. So for my bonds breaking, again, I have 4 C to H bonds. So 4 times the C to H value of 413. And I also have 2 O double bonded to O, which is shown here as 495. When I then do that math, my calculator, 4 times 413 plus 2 times 495, I get 2,642. And again, because these are the bonds I'm breaking, I'll always be breaking the bonds on the left, the reactants. That will always be an endothermic process. That gives me a positive value. Doing the same thing with the bonds I am forming. We're going to do 2 times the C double bonded to O value of 799. And 4 times the O single bonded to H, 463. 2 times 799 plus 4 times 463 gets me 3,450. These are always on the right-hand side, the products, I'm always forming those bonds. It's always exothermic, so that gets me a negative sign. And my final answer is just these two added together. So it's not products minus reactants. It's figure out your bonds breaking, figure out your bonds forming, add them together. And that gets us a heat of reaction of negative 808. If you forget the units, they're right here in the chart for you, kJ per mole. I have one more example ready to show you. If you think you feel good about this, go ahead and pause the video, go try the try problems. And if you get stuck, come back and watch the other example just to clarify some things. Okay, so for this next example, same general steps. I'm going to start by drawing my Lewis structures for everything. CH4. And then I have 2 Cl2s. Cl ends up being bonded to Cl with a single bond. But again, because of the coefficient, I'm going to draw it a second time. If the coefficient were 3, I'd draw it a third time. If the coefficient were 7, I'd draw it 7 times. Or you can multiply by the coefficient. If what I just said made sense to you, go with that. If not, draw it as many times as you need to. Then my products. We have CH2, Cl2, and we have 2 HCl's. So I have 1, 2, 3, 4 CH bonds that I am forming, or breaking, I'm going to break 4 CH bonds. I also am going to break 2 Cl bonds that are single bonds. Then I am going to form 2 CH bonds, 2 CCl bonds, sorry, that first H is a little messy. And then also 2 HCl bonds, which I will highlight now. Turning this into numbers now for the breaking, 4 times 413 plus 2 times Cl to Cl is 242. And that gets me 2,136, and it's a positive value because breaking bonds is always endothermic. For the forming, I have 2 CH bonds, which are still 413. I have 2 CCl bonds, which are 328. And I have 2 HCl bonds, which are 431. 2 times 413 plus 2 times 328 plus 2 times 431, making it a negative value because forming bonds is always exothermic, which is negative. I get negative 2,344. And to get my final answer, I'm going to add those two values. And I get negative 208 kilojoules per mole.